Alright, we are in the last section of chapter 6, so section 6.5, looking at the average value of a function. So it turns out that we can find the average value of a function f on any given interval using integration. So we find this average value, it's abbreviated f sub AVE, so it looks kind of like fave. That's f average is equal to 1 over b minus a times the integral from a to b of f of x dx. Okay, and that's it. So that is our formula for the average value. So basically you just find the value of the integral and then divide by b minus a. Right? So take the difference of the bounds and then divide. So let's look at an example. So find the average value of the function 1 plus x squared on the interval from -1 to 2. So we have f average, that's going to be 1 over b minus a, so 2 minus -1, times the integral from -1 to 2 of 1 plus x squared dx. So that's going to be, that becomes 1/3, right? 1 over 3, times, we have x plus x cubed over 3 from -1 to 2. Okay, and then go ahead and evaluate that using the FTC, and we get out just 2, actually. Okay, so the average value of this function, 1 plus x squared, on that particular interval from -1 to 2 is 2. So I want to look at this graphically, so let me separate that off here. So we can do this as kind of a side note. So let's look at it graphically. So let's see what's actually happening here. So if we look at the graph, we have 1 plus x squared from -1 to 2. Oops. So extend that a little bit. So -1, 1, 2, 1, 2, 3, 1, 2, 3, 4, go up 5. So let's see, we have the point -1 comma 2, 0, 1, 1, 2, and 2, 5. So there's our curve, as smooth as I can make it on the tablet. There we go. Okay, so there's our curve. And we're going to be looking at its area in just a second, but I also want to draw the average value we said was 2. So that's right there. Now when we look at this formula that we've developed right up here, I'm going to rewrite it in just a slightly different way. So we get the average value. I'm going to multiply the b minus a across to the other side, get it out of that denominator. So times b minus a, and that equals the integral from a to b of f of x dx. So now what does this tell us? This tells us that the area under this curve from a to b should be equal to the average value times b minus a. B minus a is just this horizontal distance, right? That's a, that's b, right? In this case it's -1 and 2. So in other words, they're saying the area under this rectangle, okay, that average value times b minus a, should be equal to the area under the curve over that same interval. Okay, so again, that's saying that they should be the same, the area under the curve and basically the area of that rectangle utilizing the average value. And if we were to find those, so do this one in purple. So that area under the curve, that's the integral of from -1 to 2 of 1 plus x squared dx. That would actually give you 6 if you computed that integral out. The area of the rectangle would be the average value, which is 2 times b minus a. 2 times 3, which is 6. Okay, so this is why we can find the average value using this formula. Okay, we just essentially with this specific example just verified it, okay, that it gives us what we're looking for because they have this relationship. So now being able to find the average value is all well and good, but we're actually going to be using this in a new theorem, and this is the mean value theorem for integrals. So we saw back in Calc 1, we have the mean value theorem, right, and that applies to a derivative, right? We have f prime of c. Now, the mean value theorem for integrals tells us something similar, but of course applying to integration. So it says, if f is continuous on AB, then there exists a number c on that interval such that f of c equals the average value of f, which equals the integral from a to b of f of x dx. So in other words, it says that the integral from a to b of f of x dx equals f of c times b minus a. Okay, so this guy right here is what we're going to be able to use. Okay, so if you remember the mean value theorem for derivatives, right, it said at some point along an interval there must be some value where the instantaneous rate of change, the derivative, is equal to the average rate of change, right? Slope of the tangent is equal to slope of the secant. Well, for the mean value theorem for integrals, it's telling us there is some point along the way here where we get the value of the integral being equal to that average value. So let's look at an example of this. So we're going to deal with the example we just worked on. So since 1 plus x squared is continuous on the interval from -1 to 2, the mean value theorem for integrals says there must be a number c on the interval from -1 to 2 such that the integral from -1 to 2 of 1 plus x squared dx must be equal to f of c times 2 minus -1. Okay. So again, it's saying there must exist a number c on that interval that this relationship holds true. Now, we've already done some of the work for this in the previous example, so we already found that average value, which is just f of c. We found the average value was 2. Okay, again, that was just from this example up here. That's our boxed answer, is 2. So, f of c, which is just this function, right, f of x, but use c instead of x, that's 1 plus c squared. That must equal 2, because of this right here. Now we can solve this for c. We get c squared equals 1, c equals plus or minus 1. both of those are in our interval of -1 to 2, so we're actually going to keep both of them, right? Just like we would with the mean value theorem for derivatives. So we can go ahead and start making our conclusion here. So thus, in this case, there are two values, -1 and 1, on the interval -1 to 2, where the MVT for integrals is satisfied. Okay, so there are two values for C, +1 and -1, where the mean value theorem of integrals is satisfied. So it has this relationship here. Alright, and that's all we're going to do with mean value theorem for integrals, just using it again as another application of integration, just going another step further. And that's actually it. Very short section to end off chapter 6. So that brings us to the end of